California is facing the worst drought in over 1,200 years. Actual measurements show that natural water reserves have dropped to record low levels. The contradiction is, this is the fifth largest economy in the world, providing 1/3 of the vegetables and 2/3 of the fruits for the entire United States. However, the agricultural sector consumes up to 80% of the fresh water, while this very region cannot provide enough water for itself. To solve the problem, engineers have deployed massive infrastructure systems, taking water from the Pacific Ocean, building industrial desalination plants, and installing modern wastewater recycling networks. The goal is to create a stable water source, no longer dependent on natural weather. So how did American engineers realize these projects? What is the actual technical process? Let's find out right now. Don't forget to press like, subscribe to the channel, and leave ideas for the next video you want us to make in the comments section. Let's get started. The first solution is the Pacific Ocean, a nearly endless water source right next to the state. However, seawater contains an average of 3.5% salt, a concentration that cannot be used for either agriculture or daily life. To separate this amount of salt at an industrial scale, engineers must build extremely complex treatment systems. First is the intake process. The biggest difficulty here is building the water intake system without affecting the marine ecosystem. Engineers use giant pipes made of carbon steel or HDPE plastic with diameters from 2 to 3 meters. These pipes are assembled and extended hundreds of meters from the shore out into the ocean, sitting deep on the seafloor. At the intake head, a special screen system is installed to prevent waste and large marine organisms from entering the system. Engineers control the water flow velocity at the intake head at an extremely low level to ensure that fish are not pulled in by the suction force. After entering the plant, seawater will undergo a multi-stage filtration process for preliminary cleaning. First, water is pumped into giant sand tanks. The purpose is to retain suspended particles, mud, and algae. Water will seep through layers of quartz sand. Impurities are trapped at the top, helping the water flow become clearer. After that, the water will be chemically treated using a metering pump system. Here, engineers will pump sodium hypochlorite for disinfection. Immediately after, they pump additional ferric chloride to perform the coagulation process. This chemical causes tiny dust particles to bind together into large clumps, helping the system easily separate them from the water flow. Finally is the step of using cartridge filters with microscopic openings from only 1 to 5 microns. Their task is to block the final fine impurities before the water enters the high-pressure compression system. The key step is the reverse osmosis, RO, process. This is the heart of the entire plant. To separate salt at a molecular level, high-capacity pumps must create immense pressure, up to 70 bar, equivalent to 70 times atmospheric pressure. Under this pressure, water molecules are forced through a semi-permeable polymer membrane, while salt is completely blocked. Because it operates under extreme pressure, the entire piping system must be fabricated from Super Duplex steel. This is a special alloy capable of withstanding compression and seawater corrosion far better than standard stainless steel. To save energy, the system installs a pressure recovery unit, helping the plant save up to 46% of its operating electricity. Finally is the remineralization process. After filtration, calcium and magnesium from limestone will be added to balance the pH and create a natural taste before distribution to the public. After leaving the treatment plant, water begins its journey of hundreds of kilometers to southern cities, through the California Aqueduct system. To construct this nearly 700-kilometer canal, engineers mobilize massive excavators and concrete pavers designed to operate 24/7. The canal bed has a surface width of 12 meters and a depth of 9 meters. To prevent loss, the entire surface is lined with a 10-centimeter thick layer of concrete using automated paving systems. This creates an absolutely smooth surface, minimizing the friction of the water flow. For hundreds of miles, this canal does not need pumps. Engineers calculated the slope with extreme precision, only a few centimeters per kilometer, so the water can flow by gravity through the Central Valley. However, this journey is blocked by the Tehachapi Mountains with an elevation of over 600 meters. This is the most difficult problem of the entire project. The solution is the Edmonston Pumping Plant. This is the largest electricity consumer in the entire California power grid. 14 massive pump units operate here. Each one is as tall as a 4-story building. The 80,000 horsepower engines create pressure to push water through 10-centimeter thick steel pipes to resist the weight of the massive water column. With a flow rate of over 8,000 liters per second per pump, this system can push water to a height of 600 meters in a single lift. This is a world record for water pumping height. Behind each pump are spherical valves weighing over 100 tons. They act as solid steel doors, closing immediately when the system loses power. This prevents millions of tons of water from crashing back, avoiding the water hammer effect that could completely destroy the pumping station. Although the canal system and pumping stations bring a massive water source from the north, California still needs another strategic backup solution. Instead of only relying on water transported from hundreds of kilometers away, major cities are beginning to be self-sufficient. They are harvesting water directly from their own drainage systems. This is when the large-scale water recycling system enters the game. California is also tapping into a massive resource right in the heart of the city: domestic wastewater. Instead of discharging it into the ocean, this water is led to the Groundwater Replenishment System, GWRS, in Orange County. It undergoes a strictly monitored 3-step cleaning process. First is the microfiltration process. Here, pre-treated wastewater is pushed through millions of hollow fibers with filter pores of only 0.2 microns. These pores are 300 times smaller than a human hair, enough to block all bacteria, suspended solids, and remaining fine silt particles. Next, the water undergoes a reverse osmosis process, similar to the desalination plant. Under high pressure, the filter membranes will completely remove viruses, salts, and pharmaceutical compounds. The final and most important step is the advanced oxidation process. Engineers use high-intensity ultraviolet light combined with hydrogen peroxide. This chemical reaction breaks the molecular bonds of the final contaminants, such as antibiotics or industrial chemicals. The result is water that reaches maximum purity, far exceeding standard bottled water specifications. Instead of being led directly to taps, this water is pumped into underground aquifers to replenish groundwater levels. It also creates a pressurized water wall to prevent seawater from intruding into the mainland. From separating ocean salt and operating the world's highest pumping station to the ultra-pure water recycling process, California has built one of the most complex and robust water infrastructure networks on the planet. These megaprojects are not just engineering achievements, but vital factors for maintaining the world's 5th largest economy. The synchronized combination of all three solutions, desalination, water delivery, and recycling, ensures stability. Even in the driest years, agricultural and daily life activities in the state remain stable. Don't forget to like and subscribe to the WIN channel to explore the engineering secrets behind the world's greatest megaprojects.